Welcome to this cinematic explainer. Imagine for just a second that the soft, golden light of sunset here on Earth fades away and is replaced by the vast, mysterious, ancient theater of the cosmos. Today, we're embarking on an epic natural history documentary of the universe itself. We're strapping in for a premium interplanetary safari using real astrobiology to explore 3 breathtaking theoretical worlds. I am absolutely thrilled to be your guide through this heritage-style journey into the unknown. We're going to blend the rigorous laws of physics with the awe-inspiring beauty of what could literally be out there.
Okay, let's dive into this beautifully complex question. What do real aliens actually look like? You know, when we picture alien life, Hollywood usually gives us green humanoids. But to understand what real extraterrestrials might look like, we just need to look at the staggering, almost magical diversity right here in our own ancient world. Earth has birthed organisms in the strangest of places. We're talking magnificent blue dragon sea slugs drifting in ocean currents, to incredibly rare snails clad in literal iron shells near deep-sea hydrothermal vents. The wild history of life on our planet proves that nature is fiercely creative. So what happens when we take that creativity and project it across the stars?
To anchor our imaginative journey in real, observable science, we have to look at extremophiles. These are organisms that thrive in extreme physical or geochemical conditions that are detrimental to most life on Earth. And this brilliantly illustrates the sheer tenacity of life. These aren't just surviving, they are actively thriving in environments that would be instantly fatal to us. Boiling acid pools, frozen glaciers, the crushing pressure of the abyssal deep. By studying the biological engineering of extremophiles, we can mathematically and biologically deduce exactly how life might adapt to the absolute harshest environments in the galaxy. To keep us focused, here is today's flight itinerary. First, we'll plunge into Inchba, the dark ocean. Next, we'll soar through Nimbus and its living clouds. Then, we brave the freezing environment of Moniere, the magnetic moon, before returning home to reflect on the value of all this speculation.
All right, first stop, Section 1, Ayapa, the dark ocean. Life in the eternal twilight.
Picture a tidally locked ice planet, forever caught in a staring contest with its dim red dwarf star Oculus. One side is locked in frozen night, the other in an eternal, dim glow. Notice the stark contrast in the physics of light here compared to Earth. On Earth, bright white sunlight makes our plants reflect green. But Oculus is incredibly dim. The plants on ISPA must absorb every scrap of weak infrared light just to survive. Because they reflect almost nothing back, this entirely alien flora appears deep, pitch black.
This leads us to the heart of this world, the Eye of ISPA. This is a warm, 200-meter-deep black ocean, churning with never-ending surface storms but harboring perfect stability below. On the surface, it's a theater of absolute chaos. You've got this violent storm where blistering hot air from the center collides with freezing winds from the dark, icy outskirts. But as we slip beneath those churning waves, the cinematic turbulence just fades away. Below, we find a calm, pitch-black underwater jungle. A perfectly balanced ecosystem that has remained virtually undisturbed for billions of years.
Now, what's really fascinating here is the ecosystem of this dark murk. Because there's so little light, absolutely nothing down here has evolved eyes. They navigate this ancient murk entirely through sound and texture. Imagine a sprawling forest of black kelp, navigated by streamlined, blind grazers, kind of like gentle underwater cattle. But lurking in the dark fronds are camouflaged predators, lethal leaf mimics waiting to strike. The seabed is alive with seed eaters, which are these mud pokers with snapping pincers. Then there are squeaking, poison-loaded flora called spike bulbs, and flailing, starfish-shaped hunters we'll call grabbers. Together their clicks, squeaks, and movements create an unsettling, unending biological symphony that is echoed in the deep for eons.
Leaving those oppressive depths, we travel to Section 2, Nimbus, the living clouds. A story of buoyancy and impermanence.
Bathed in the searing, blinding blue light of a massive star, orbiting Nimbus, a colossal water-rich gas giant. Just think about this number for a second, 900. Nimbus is showered with 900 times more light than our own Neptune. This immense, relentless solar energy cooks the atmosphere, generating titanic, warm updrafts that rise from the hazy depths, lifting moisture into gigantic, swirling white clouds literally the size of continents. And astonishingly, inside these atmospheric oceans, life has found a way. High up in these majestic clouds, an incredible aerial food chain has taken shape.
You have quadrillions of microscopic cloud plankton, about a millimeter in size, drifting on the air. Much like tiny spiders on Earth, they spin wispy electrostatic threads, surfing the electrical charge differences between the top and bottom of the clouds while feeding on airborne sulfur and nitrogen. But they aren't alone. Darting through the mist are jet squids. These are frog-sized predators that use rocket-like gas bursts to launch themselves. They are vampiric, violently hunting for the sky's most precious resource, stolen nectar.
Let's move on and see how this builds into something truly colossal, the mechanics of a sky whale. To stay aloft forever, life on Nimbus evolved living hot air balloons taller than Earth's grandest skyscrapers. First, they trap atmospheric gases in a wafer-thin membrane. Second, they filter feed plankton to generate intense internal heat. They drop massive, sticky nets into the clouds to catch that electrostatic plankton, which is burned in specialized glands. Finally, this expands the trapped gas, allowing them to achieve permanent buoyancy, to float infinitely. Oh, and the leftover food? That becomes the rich nectar that jet squids are so desperately hunting.
Yet for all its sweeping cinematic beauty, the tragic fate of Nimbus is sealed. Unlike the billions of years of stability on Ipa, Nimbus is doomed. Hot blue stars burn furiously and die incredibly young. 600 million years ago, life rapidly emerged in deep water droplets. In the present day, complex cloud ecosystems thrive. But 10 million years from now, a blink of an eye in cosmic terms, its star Caroleus will burn through its fuel and consume the planet. It begs the question, doesn't it? Is it a tragedy that this world ends so soon, or a miraculous stroke of luck that such a breathtaking choreography of life existed at all?
From those doomed clouds, we jump to our final destination, Section 3, Monye, the magnetic moon, a completely frigid, frenetic world.
Monye orbits a massive brown dwarf, its sky dominated by sweeping, colorful auroras. The gravity here is an incredibly weak 5% of Earth. But what really drives the chaos here is time. Monye orbits its brown dwarf in just 3 hours. The days and nights are blindingly fast. As the freezing night hits, dry ice literally snows from the sky. As the brief daytime sun crests the horizon, multicolored liquids erupt from the ground in sudden bursts of cryovolcanism. It is an environment of intense, rapid extremes.
So, the crucial point is the biological foundations. How does life adapt to survive this? Well, Earth relies on liquid water and steady solar energy. But on Monye, water would freeze instantly during those rapid nights. Instead, life here relies on toxic liquid ammonia as its solvent. And because the moon is rich in iron and lead from an ancient metal nebula, life has evolved to physically harness intense magnetic fields for survival.
This creates a frantic race against the setting sun. Look at these astounding creatures and their unique adaptations. First, skyflowers. These brittle plants levitate 1 kilometer high using magnetic minerals. Because of the 5% gravity, they literally repel against the moon's magnetic field to float into the sky, desperate to catch a few extra seconds of sunlight. Below them, you have skaters. They circle the moon dragging magnetic kites, continuously outrunning the sunset so they never freeze. But hiding in the jagged crystalline ground are the ambushers. They hide as crystalline landmines with electric whiskers, violently snatching the skaters as they zoom past. It is a stunning, high-stakes drama played out every 3 hours.
Let's leave that freezing chaos behind. We arrive at Section 4, the value of speculation, and a look back at Earth.
After soaring through eternal dark oceans and magnetic snowstorms, our homeworld feels uniquely warm and precious, doesn't it? But as we look up at the countless twinkling lights scattered across the night sky, we really have to ask ourselves, will we ever witness these exotic oceans or metallic animals? The universe is unimaginably vast, and what we've explored in this explainer today is heavily grounded in the very real rules of biology and physics. The odds tell us that somewhere, right now, alien life is living out its own magnificent documentary.
I want to leave you with this final, inspiring thought. Scientific speculation gives us ideas about what we should look out for. Exploring these theoretical worlds isn't just about entertainment. By pushing our understanding of extreme biology and distant astrophysics to their absolute limits, we are actively preparing our minds for the true cosmic mysteries waiting for us. We learn what signatures to search for, and we expand the boundaries of what we believe is possible. So, what other breathtaking secrets is this universe hiding just out of sight? Keep your eyes on the stars, stay curious,